What are the different types of sampling techniques are there? So there are different sampling techniques are there. So at a high level, there are two branches. One is the probability sampling technique and sampling probability technique, or non-probable sampling technique. Within the probability itself, we have four different types are there: simple random sampling, stratified random sampling, cluster sampling, systematic random sampling. And in the case of non-probability sampling, you have the convenience and quota sampling. I wouldn't recommend these two because it is very time data. Okay, we work most of the time with the real-time data. Once again, okay, hence this is not recommended one. So let us take a look at, or let's dive into each and every type of these sampling techniques. To start with, let us understand what is simple random sampling. So this is your population. Okay, so in your population, you make sure that you are picking up every item in such a way that it has an equal chance of being selected. Every item in a population chosen in such a way that every item has an equal chance of being selected. That is what your simple random sampling. Okay. So in this case, what are the advantages? Easy to draw unbiased. Easy to draw because you close your eyes, you randomly sample here and there. See, if you could have seen the television program, right? So there are some kind of program in a television. You might have seen this one. There will be some competition. Two different people will be, arguing, or they participate in the contest. At the end of the contest, right? They will ask them to come and shuffle all the papers. They write each and every person name in a paper, and then they fold it and then put it in a big jar. And then they ask them to come and shuffle it first, right? Why do they need to shuffle it? So that every item or every person name should have an equal chance of being selected. That is the reason why they're shuffling it. Okay. And then you randomly go and you call some people in the audience, from the audience, and ask them to close their eyes, and then pick up 3 or 4 papers or sheets from that thing, folded sheet papers, right? All ask them to pick it. That is what your simple random sampling. So if you shuffle it, what will happen? Every item in a population, has an equal chance of being selected. That is what your simple random sampling. But when you close your eyes, right, randomly when you select it, what will happen is it may not be representative. It may not cover all these segments. Like in the previous example, high income group, medium income, low income group. If you close your eyes and pick up the thing, right, there could be chances you might be picking up the people name from the high income group only. Hence, it may not be representative. There will be a huge variance, but very easy to draw. Hence, it is unbiased because you are closing your eyes and it is got shuffled already. To make sure that everyone should have an equal chance of being selected, you're shuffling it. You close your eyes and you randomly pick up. Very easy to draw. It is unbiased. If I don't, close your eyes, what is going to happen? And again, only 10 contestants are there. What is going to happen? There is a question, how does the sample is being identified? I mean, the type of sample being required. That we'll discuss it later. First, let us understand the pros and cons of each and every type of sampling. Then you will understand what sampling technique is, what sampling technique to be used when. Okay. Supposing you don't have, much, your volume of the data is very, very huge, very, very huge. In that kind of situation, and again, you need to make decision quickly. You don't have time to draw even the huge sample. And again, you don't have access to the entire population data. Then you are left with simple random sampling technique only. Obviously, it has some kind of bias with it. Okay. But you need to, you need to specify the assumption saying that, I don't have access to the population data, and all segments of data also, I don't have access. Since given the time constraint, we have used the SRS technique, simple random sampling technique. It's a good question. Okay. And next one is stratified random sampling. So every group is represented proportionally to its relative size in population. For example, this is what your population, and you have 3 different groups of people out there. Okay. So here in this case, how do we draw the sample? So we have divided this entire population into 3 different groups. For example, this group of people are having an affinity towards a specific Samsung brand, and these people are having, a very affinity towards iPhone, and these people are what other brand? We have something like Motorola or something like that. Okay, Motorola, or the MG, right? Samsung, MG, or iPhone. So these people are having brand affinity. What you are doing is you are going to draw a sample from all these 3 groups. Your sample should be a representative of the population. In the case of stratified random sampling, what we do is we draw a sample from all the groups. How do we draw the sample from? The next question, how do we draw a sample from these 3 groups? Can I draw here 1, 1, 1, or can I draw 5 and 5 and so in this case, each group is represented proportionally to its relative size and population. Relative size and population. Supposing you have, for the sake of simplicity, let's you have 10 customers. Let's 10 customers you want to randomly sample it. Your sample size is 10. But your sample is supposed to be representative. What do you mean by representative? You need to randomly sample the customers from all the 3 groups. Okay, in this case, here I have 5 and 3, 8 plus 2, 10. Can I say 5, 3, 2? 5, 3, 2. So let's assume that, let's say you have 100 customers are there. Let's, here you have 100 customers, out of which 50 customers are Samsung, and 30 customers are iPhone, let's they are MG, and 20 customers are iPhone. Okay, so your sample size is 100. Okay, out of which this is, sorry, let's assume that this is your population size. Okay, so this is your population. In your population, you have 100 customers are there. 50 customers, they bought Samsung, and they have more affinity towards Samsung brand only. Okay, they may hold more than one mobile phone, but all the mobile phones belongs to Samsung. The same customer, he may be having more than one Samsung brand he bought it. Okay, that's how brand affinity, in the sense these customers, they are very particular with Samsung only. Okay, so if I ask you to draw the sample with the size 10, what proportion you are going to draw the sample from these 3 groups? 10, right? So out of 10, 5, 3, 2, because you have more people, right? So 5, 3, 2. So in this case, with the proportional sample, so sorry, the with proportion to the population, right? The sample also should have the proportions of your population, or in other words, the sample should have the proportions similar to that of your population. Here 5:3:5:2, right? 5:3:2. So in that is how we need to draw the sample. Your sample should be the proportion of your population's size. Okay, the sample size should be proportion of your population size. Okay, that is what called as stratified random sampling. Okay, and the question is, okay, is it always mandatory? They said there are some cases my group is represented disproportionately to its population. So in the previous case, yes, let's say you have 500, 300, 200, but here if you see 200, 400, 600, 800. With the disproportional sample, the sample need not to have the same proportion as your population. Need not to have the same proportion as your population. Supposing if I ask you to draw 10 samples from this population, what will happen? If you go by the proportion, here if you draw 8, and 642, what will happen? Here, if you see, very less number of customers are there, right? You have very less number of customers. Your sample size should also be reasonably good. If it is very less, then your outcome will be whatever the test that you conduct with the sample that have less number of data in it, it can lead to some kind of bias. Okay, so with the disproportional sample, with disproportional population, the sample need not to have the the sample your sample need not to have the same proportion as the population. So you can, in that case, you need to use your common sense, right? You need to use your common sense. So if somebody is asking you to draw a sample, something like, 10 or let's say 20, if they ask, right? You can tell them 10 is not possible. And it is going to be, very small samples. So let's say if they ask you, let's say 100 samples, you can make sure that you have reasonable amount of people selected in this group also. Like I said, in simple example, 10, if you 8, so let's say 20, right? 8 plus 10, 20. So your sample size is 20, but in this population, you have selected only 2. This sample size is very small. In this group, you've taken very less number of customers. Obviously, it can, it will have a bias towards the higher values in your sample, right? So make sure that in the case of disproportional sample, you need to use some kind of common sense, and then you need to draw the sample. For example, your sample is 100. Make sure that in this population, you are drawing more. Okay, listen here, you are going to draw at least 50 and 40, and here you can say let's say in this case 20. Here you 20 and 40, right? So 40, 60 and 20, 20. Okay, here you can 20, 20, something like that. Okay, so it should be reasonable. If you put 2 here or 4, very less, right? Make sure that each group also have reasonable amount of samples in it. The sample size are too small, your test result, statistical test will not give you it will mislead you, your sample test output. One second, please, I'm getting it. Drawing sample across all the group. Whereas here, in the case of simple random sampling, you are closing your eyes, or in simple term, right? You are randomly sampling the data, right? Randomly sampling. When you randomly, it's something like you are closing your eyes and picking up the items from or objects from this sample in the population. In that case, what will happen? There could be chances you might miss out some specific segments data while sampling it. So hence you tell me which one is good. In most of the time, the stratified random sampling is the one we do it. Okay, this is the one is advised one. And there are some situations you don't have access to all the 3 groups. Then you have to go for SRS, simple random sampling. The next one is the cluster sampling. What is cluster sampling? In the case of cluster sampling, we divide the whole population into groups like stratified sampling. Here also, we are going to divide the entire population into clusters or groups. Groups also called as clusters or clusters, okay? And even in this case, a random sample of cluster is selected. For example, in this group, in the population, there are 2 different groups of people. These people always prefer Samsung and these people always prefer iPhone. Or, okay, this is not the correct example in this case. Okay, what we will do is, what we will do is we'll take the high school students in a large city. Okay, instead of selecting individual students from all schools, we will randomly select a few schools from different regions in the city. So this is your north region, and or there's some group of schools. Let's or the area. Let's this is your entire Mylapore, and this is your Adyar. Okay. Instead of selecting individual students from all schools, we randomly select a few schools or clusters from different regions in the city. Then you collect data from all students within the selected schools to represent the entire. So in this case, simple thing is we have one more cluster is a group, and these people are from Aryapuram. These people are from, or these people are from Besanagar, Adiyar. These students, right? Okay, schools, group of schools. It's not an individual school. Group of schools in Besanagar, group of schools in Adiyar, group of schools in Mandeveli. What you do is you divide the entire problem into groups and randomly select any one of the cluster. So these are groups are nothing but clusters. Okay. So I'm going to randomly select this one, Mylapore. Okay. Or maybe randomly I can select this one, or I may randomly select this one also. You select any one of the, divide the population into groups, and then you randomly select a cluster. And then what you do is you run a survey, or you collect data from all students in this cluster. In Mylapore, you collect data from right, all the students studying in all the schools. All the students from your Mylapore. Okay. So instead of going and collecting the samples from each and every schools or each and every individuals from each and every school, what you do is you create a cluster or group. In this cluster, all the schools in Mylapore, all the schools in Adiyar, all the schools in Besanagar. And then what you do is you take any one of the group randomly, and then you run a survey with all the people in that specific cluster. This is what your cluster sampling is all about. Now the question is, when can I use the cluster sampling? So what is the advantage of this? What is the disadvantage of this? So here also there could be chances when you create a cluster, it may not be representative of your population. Okay. Another aspect is, right, if you think collecting the samples from all the students from all the schools in all the locations is very costly prohibition, right? Cost wise, it is highly prohibition, right? So in that kind of situation, you can go for cluster sampling. If the cost is too high, so this is a simple way of doing it. The other simple example is, for example, you are running a hotel somewhere in a holy place, somewhere in the, let's say, the holy place, right? Holy place. A temple is there, and a specific event like Masi Magam. I guess all of you people are familiar with this festival in Kumbakonam, right? In Kumbakonam, this festival will happen. So that time, a lot of pilgrims, they throng this temple, Kumbakonam temple, take a bath, right? So in that case, let's you have a hotel there. It is a 10-story hotel. Customers from across south, northeast, south, across India, they come and book the hotel at least 1 week in advance before the festival starts. At least 4 to 5 days before the festival starts, they come and book the hotel. You just think that way, okay? And very well, as a hotel owner, majority of them are South people, okay? And there's a majority of the South people, and North, a few of them are North, and something like that. You can well, let's say South and North, okay? So what you do is you go by, you have 10 stories are there, you offer a complimentary breakfast. You offer a complimentary breakfast, and each floor you have at least 17 rooms are there. Each floor you have 17 rooms are there. So you want to understand, okay, what is the customers feel about the complimentary breakfast in terms of the quality, taste, everything. What you do is, instead of sending your person to run a survey to each and every floor, you take the entire first floor or any specific floor, and you send a person there. Ask each and every roommate, 17 roommates, you need to run a survey and get the data. That's all. Okay, this is another scenario where you can use cluster sampling. Okay. So you have 17 rooms. You remember that. In this case, almost obviously, right? People from South and North also. We have a mix of, the different regions also will be, occupied in the first floor itself. Okay. So in that kind of situations, you can go for cluster sampling. Seeing any other examples for this. Okay. One second. Okay, any other example? Like, let's you want to run a customer satisfaction survey for a large retail chain with stores spread across the country. So in that kind of situation, you can employ cluster sampling. Okay, within India, you can take the few specific cities, right? Or you can randomly select few stores as clusters, few stores as clusters, or within Chennai, right? Within Chennai, you can randomly select a few stores as clusters. Okay, and let's say cluster 1, cluster 2, cluster 3, and then survey all customers who visit those selected stores during a specific period to gain insights into customer satisfaction for the entire retail chain. Okay, so in that kind of situation also you can go for cluster sampling. Okay, in this kind of situation you can save cost and some extent time also, because you are grouping set of retail stores in a cluster, right, in the some location. All the stores in some location, you are grouping it and you are doing it. In that kind of situation also you can go for the cluster sampling. And what are the sampling techniques to avoid? The convenience sampling and judgment sampling, these are very biased one. But anyhow, for you people to understand what are the different sampling techniques, I just mentioned this one also. And I wouldn't recommend to use this kind of technique. one is the central limit theorem. I'm going to talk about the important concept called central limit theorem. So what is central limit theorem? In statistics, this is one of the important concepts. The central limit theorem, it states that regardless of the shape of the distribution, the sampling distribution of sample means approaches a normal distribution as the sample size gets larger. So here, right, again, so there is another version of the central limit theorem. Okay, as the sample size increases, the distribution of the sample means approaches a normal distribution with the mean nearly equal to population mean and standard deviation equal to sigma n. Okay, and also the another rule is as the sample size increases to, as the sample size, increases to 30, it becomes approximately normal distribution. See what here he says is, this definition, what it says is, so here your normal distribution, we already discussed about different types of distribution: normal distribution, uniform distribution, skewed distribution, random distribution. Okay, random distribution, something like this. Okay, and normal, uniform, skewed distribution, always, this is your right skewed distribution. Okay, these are, okay, right, something like, or this is exponential distribution. So each and every population distribution, when you take the population data and if you plot it, for this population, it's a normal distribution, it's a uniform, it's skewed distribution, then this is exponential distribution, something like that. But when you draw sample 10, irrespective of the shape of your population distribution, you'll find something like this, right? So look here, it is not showing anything good, right? It's something like a triangle. But when you draw sample somewhat close to 30, irrespective of the type of your population's distribution, it becomes approximately normally distributed. It becomes approximately normally distributed. So how is it possible? How is it possible? Is it possible? For example, I just show you here with this data already, I have it. Look here, in this case, if I take only these three values, this is my, okay, I just remove this chart. Let's say you have a population, but make sure that when you draw a sample, you're drawing the sample from the same population, okay? If your population is this one, you need to draw a sample from this one only. If your population this one, you need to draw a sample from this one only, okay? So your sample is supposed to be from the same population. And here, let's all these values are falling in this. Let's assume that in the normal distribution, this is a normal distribution. So what I do is I just draw 3, 5, 8, and 10 only. Let's say this is not a population, actually, it is a sample only. Your population will have some more data. Let's say we start with, initially we started, drawing few samples, 4. And then what I do is I just go here, insert, and I'm going to create a histogram to view whether it's a normal distribution or not. Here I just go here, insert, and I just select this one. I'm going to use it. Is this a normal distribution? No, right? This is not a normal distribution. What I do is I'm going to draw, in addition to this, I'm going to draw some more sample from a population. And then what I do is I'm going to select the data from this one. I'm going to increase my sample size to, I'm going to increase my sample size. One second. In this case, let me select the data. Okay. What I will do is, when I selected this, it was not a normal distribution. Let's assume that this is my population. Okay. And in this case, I'm going to take some more data. Okay. What is wrong with this? It was showing correctly here. Okay, let me, okay, I have taken from here. Okay, not this one. 6.5 and 10, 17.75. And for this one, Okay, we will, okay, I think in this case, I've taken the data from here. Up to Q12. Okay, this is the one I've taken it. Okay, for this one. In this case, for example, if I take a few values here, and then if I go and select it here, it will be something like that, right? So if I select only these three values, what is going to happen? The whole idea is, as you increase the sample size, it will become approximately normally distributed. That is the whole idea here. That this is the one, right, found out by someone, right, some scientists. It's really helpful. How it is helpful, that we will discuss it, as part of the confidence interval. There is something called confidence interval. Look here, as you draw more samples, it becomes approximately normally distributed. But in this case, when you select only three records, instead of this, if you select up to this one only, it is not normally distributed, right? As you draw more samples, it becomes approximately normally distributed. And what central limit theorem says is, if you draw a sample, as you draw a sample close to 30, irrespective of the shape of your population distribution, your sample will become approximately normally distributed. Let's say, your population distribution, uniform distribution. When you draw sample 10 or something, it will not be, that good. And when you draw somewhat closer to 30, it will become approximately normally distributed, irrespective of your population distribution. When you draw sample, when your sample size is 30, it is going to be approximately normally distributed. That is what this theorem tells us. So that's what is, as the sample size increases, the distribution of the sample means, the distribution of sample means, this is another thing, okay? The sample means, the sample means approaches a normal distribution. The sample means also approaches the normal distribution with the mean nearly equal to population mean and standard deviation equal to sigma divided by square root of n. So, okay, what I will do is, I will just show you with this example. So what you need to remember is, so these are like your sample means, okay? When you plot your sample means, it will become approximately normal. This is one point you need to remember it. Apart from this, look at this as these values are from your population. Like I wrote it earlier, right? If you draw a sample size 2, what are the possible combinations how many possible combinations you can draw sample here? You remember it in the PowerPoint I have shown you, right? 1, 2, 3, 4. So 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, right? So likewise, how many samples we can draw? 14 samples we can draw here. 14 samples we can draw here. We can draw 14 samples. Each sample, we compute the mean and then we note down the mean. When you plot all these means, sample means in a distribution, that is called your sampling distribution. When you take an average for the sampling distribution, you are getting 2.5. Your sampling distribution's mean value and your population mean value is same. This is what this is also one of the central limit theorem, one of the principles of your central limit theorem. Whereas the means of all the means of your sample distribution's mean is equivalent to your population mean. It is as simple as that. See, if you ask me to draw a sample again, right? So here with replacement, let's say I want to draw, let's say my sample size is 2. With sample size 2, how many number of possible combination of samples we can draw here? So 1, 1, 16, right? 1, 1, and other sample is 1, 1. Sorry, 1, 1, 1, 2, 1, 3, 1, 4. 1, 2, 1, 3, 1, 4. What does it mean for this? Is sample 1, sample 2, sample 3, sample 4, right? And the next one is 2, 1 and 2, 2, 2, 3, 2, 4. Guys, this is the very simplified version. If you see it in the internet, you will get confused literally. Okay, you will understand, but it takes a lot of time, right? So 2, 1, 2, 2, 2, 3, 2, 4. And next one is 3, 1, and 3, 2, and 3, 3, and 3, 4. And similarly, 4, 1, and 4, 2, and 4, 3, 4, 4. So how many samples we have? 16 samples. Each sample, if I compute the mean, how many means I will have it? 16 means. Already I did it. To make your life simple, see, for each sample, I computed the mean. And again, I'm taking the mean on all these samples mean, 2.5. This 2.5 is equivalent to my population mean. This is my mu. This is my population mean. This is my sampling distribution mean. Here they use different notation. X bar is sample mean. Sampling distribution mean is SX bar, I think so, right? So this is 2.5. So your population mean is equivalent to your sampling distribution Xi, your sampling distribution mean. That is what it tells us. If you go back to the theory here, the definition, as the sample size increases, which means 30, the distribution of the sample means also approaches a normal distribution with mean nearly equal to population mean and standard deviation equal to sigma equal to, the normal distribution mean nearly equal to population mean. The sample means approaches a normal distribution with mean nearly equal to population mean. That is what it tells us. So here, right, regardless of the shape of the distribution, the sampling distribution, sample means approaches normal distribution. But here I have elaborated this in detail. So the population mean is equal to standard, the population mean is equivalent to your sampling distribution mean. And at the same time, your sample means will approach as a normal distribution as the sample size gets larger. So in this case, what happened? In this example, okay, I did something nonsense here. 1 second. In this case, I have taken a few samples here. In this case, okay. So in this case, I have taken few samples here. So here I have 3, 5, 8, 10, 12, right? In this case, what I did, what is the population mean here? The population mean is 13.8. Average is this one. Let's assume that this is my population data. And then here it comes around close to 14, right? If I do 14. And if I draw 3, 5, 8, 10, if I, what is the average of this one? We can see that average is 6.5. That's what I put it here. If I draw a sample, first sample, 6.5. And then if I take 5, 8, 12 in another sample with the replacement, sorry, 5, 8, so in this case, 5, 8 and 12 and 15 I have taken. In this case, the average is 10. Okay. Likewise, I have taken, different, okay, I just put it here so that you'll be able to understand. And here I have taken 3, 5, 8, 10 as my sample one. In my sample one, I have taken this value. Okay, so for example, here 3, 5, 8, and 10. I have taken this value. And the next one is 5, 8, 12. 5, 8, 12, 15. And 8, 18, 20, 25. So for this is the average. So in this population, I have randomly sampled the data. These, and randomly samples. This is sample 1 and sample 2, sample 3. I randomly sample the data and computed the mean for each and every sample. When you plot these, the sample mean, when you plot the sample mean, it becomes approximately normal. Okay. So we have randomly sampled the data from the population and I calculate the mean for each sample. Okay, and then what we did here, with this 10 data points in the population and the small size samples, right? 4, each sample size is 4 only. You can see, some kind of normal distribution here, right? The sample means of the sample means when you plot it in a chart, as you, for example, if I plot only few samples here, sample means. Only few sample means it is not approximately. As you draw more samples, it becomes approximately normally distributed. So this one relates to my first principle. What is my first principle? As the sample size increases, your distribution will become, approximately normal distribution, especially irrespective of the population distribution. When you draw a sample which is closer to 30, it will become approximately normally distributed. Okay, when I draw random samples from the population, and then when I plot these samples mean in the chart, it becomes approximately normally distributed. As the number of samples increases, the sample means, if I increase the sample size, number of samples, and each samples means when I plot it here, as with the more samples means, it becomes approximately normally distributed. Apart from this, the sampling distribution mean is equivalent to the population distribution. Sorry. Yeah, as the sample, irrespective of the population distribution, if the sample size becomes 30, it will become normally distributed, property 1, and that is what it is, right? And the property 2 is when the sample means, right? The sample distribution of sample means approaches a normal distribution as the sample size gets larger. That is what this example, okay, that is what this example tells you. Okay, as with 3 samples means, if you plot it here, it was not normally distributed. I increase the number of samples. 6 with 6 samples means when I plot it, it becomes approximately normally distributed. And another point, what he says here is, as the sample size increases, the distribution of sample means approaches normal distribution. Yeah, it talks about sample means only, with the mean nearly equal to population mean, and the standard deviation equal to sigma divided by square root of n. The sampling distribution mean is equivalent to your population mean. Okay, that is what we have seen it. And at the same time, your population standard deviation is equivalent to your sampling distribution's standard deviation. How do you find out the sampling distribution standard deviation? Sigma divided by square root n. Sigma divided by square root n. This is called your error. How far each value is away from your mean. That is what your standard deviation. So here, okay, now the question is, why do I need to learn central limit theorem? See, in this case, we have drawn many samples, right? Look here, if you see here, here in this case, if you forget about this case, if you look at these 4 values, this is my population values. In my population, let's say hypothetically, I have only 4 values. To draw sample size, let's each sample size 2. And if I wanted to draw, if the sample size 2, how many possible combination sample we can draw? 16 possible sample. In this case, you need to draw 16, all the possible combination samples, and you need to find out each sample's mean, and you need to take the mean of all the samples mean. Do you think it is practically possible in the real-time scenario? In the real-time scenario, do you think in the population we have only 4 values in it? No, right? In the population, we have huge volume of data. Okay, you cannot draw all possible combination of samples from your population. Okay, we never actually create a sampling distribution that would require a huge effort since we cannot afford to take multiple samples. So what we do, based on a single sample, is it possible to make inference about the population mean? That is where right? So that is where there is something called confidence interval estimation and hypothesis testings are coming into picture. Okay, based on a single sample itself, is it possible for me to make an inference about the population mean? That is where there is some, yes, it is possible. That is where there is a concept called confidence interval estimation and hypothesis testing comes into picture. These are the engine driving, so the engine that drives these tools like confidence interval estimation, hypothesis are called your central limit theorem. You understood, right? Instead of drawing all possible combination of sample from a huge population, it is practically impossible. Is there any way can I use a single sample to make an estimation about the population mean? Yes, that is where we have some other technical confidence interval comes into picture. The engine driving this confidence interval is nothing but your central limit theorem. With this, I'm going to stop. As of this one, the confidence interval, we'll discuss it in the next session. Okay, next week and we will continue. Next weekend, we are going to increase the duration also. That I will get back to you about the timing of obviously, if I start by 9 p.m., it will be too late. We'll get back to you about the schedule, everything. Okay. With this, I'm going to wrap up. Before I wrap up, a quick summary about what we discussed. Okay, we discussed about what is inferential statistics all about. And also I discussed about what is population and what is sampling. And also we discussed about sampling distribution. And also I discussed about the central limit theorem. Okay. And different types of sampling technique also I discussed. Followed by that, we discussed about the central limit theorem. Any questions so far? Okay, since you don't have any questions, I'm going to wrap up the session. You need to watch my video. So it is not that they blindly came up